We're asked to calculate an approximate value for the following quantities using the linear approximation around x sub naught equals 9. So we need to find for part A, I'm going to do maybe 2 of these and I'll let you do the other 2 yourself. So for part A, we want to approximate the square root of 9.02 by using a linear approximation at an initial value of 9. So let me go ahead and draw what that function looks like. So the square root, we're going to be using the square root function. And so it looks something like that. And so here, at a value of 9, the height value is 3, because we have the square root of 9 is 3. Okay, pretty simple. Now what we need to do is we need to get an approximation for this guy right here, which is 9.02. So what we want to know is what is the height. What is the square root of 9 point? So 9.02 comma what? This is the guy that we're getting an approximation for. So what we're going to do is we're going to take our tangent line, put it in there. Now the tangent line is going to, that linear approximation is going to overestimate what the square root of 9.02 is. So doing the square root of 9.02, now we can do it on a calculator, right? Okay, or there's an algorithm for it as well. Okay, but let's say we want to do it real quick and we want to get an estimate for it because we don't need to be super exact. So what we're going to do is we're going to take the derivative of f of x. So the derivative of the square root of x is 1 over 2 square roots of x, which implies that the derivative, the slope of this tangent line right here at 9, because 9 is the point that I'm going to use for my x value, that's equal to 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 1/6. So the slope of the green line is 1/6. Okay, now what we need to do is we need to go over to 9.02. So to get over to 9.02 on the function here, this length, this green length right here, that's dy. So dy is going to be equal to f prime at 9 times delta x. Well, this guy right here is delta x. So delta x is 0.02 and f prime at 9 is 1/6. So I've got 1/6 times 0.02. That is going to be dy, which is equal to 3.0033 and so on. Okay. Whoops, sorry, that's not equal to, I said that wrong. I wrote down the answer here. This is 0.02 over 6, which is the same as 2 over 600, which is 1 over 300. And if we take 1 and divide it by 300, we get 0.003 repeating. So this is 0.003 repeating. That's this green length right here. Okay. So the height of the green length, okay, this height is going to be this length right here plus this length right here. Well, we know this length right here is 3, so this is going to be 3 plus the green length, which is 0.003 repeating. And so the best estimate that we have for the blue question mark height is 3.003 repeating. That's as close as we're gonna get to it with this approximation. Okay, so that's not too bad. Now we can go ahead and check to see how close this is, because if we take the square root of 9.02, here's my square root button. I know it's here somewhere. We get 3.003331. So it doesn't differ until we get out to this spot right here. So this right here is really, really close to the value that I wanted. Okay. Now I also want you to notice that the actual change in y, if I just subtract 3 from this, the height, the actual change in y, here it is, and here was dy. So delta, this is delta y, this is dy. Okay, now let's go ahead and we'll do one more. So I'll do b here for you. So b asks us to do the same thing, but this time to approximate the square root of 10. Now the approximation here is not going to be as good because 10 is further away from 9 than 9.02 was away from 9. So if we take a look at the graph again, and this is something that's important to look at here. So f of x is equal to the square root of x. So if here is 9, not to scale, and we come up, we know that the square root of that is 3. Now, here is 10, and we know that this guy up here is the square root of 10. And that's actually what we're looking for. We're looking for an approximation for the square root of 10. Okay. When we had 9.02, what I want you to notice is once I draw in my tangent line, okay, once I draw in my tangent line, 9.2, the difference between the actual function and the green line is not very much here when these guys are close to one another. But when they're further apart from one another, the difference here between these 2 points, this is greater than this. So what it tells us is that our linear approximations are better the closer we are to our initial value. Okay, so this number is not going to be as close as the last one was for the approximation. So again, we need the slope of this line, and we already know, I'll just do it again for you, but we already know that f prime of x is equal to 1 over 2 square roots of x, which implies that f prime at 9 is equal to 1 over 2 square roots of 9, which is 1 over 2 times 3, or 1/6. So we, just like last time, we know the slope of this guy is 1/6. Now, to get dy, geometrically, this whole length right here is dy. So dy is given by f prime at 9, which we've already got. It's the derivative at this point right here. Okay, that's the slope of the line, times delta x. So dy is equal to f prime at 9, which is 1/6, delta x, which is the change in x, which is now this length right here. It's the length over the run, which is 1, so it's 1/6. And 1/6, guys, if I take 1 divided by 6, I get 0.16 repeating. Okay, so this is 0.16 repeating. So what it says is that the total length up, our approximation for this guy in orange, I'll do it in blue, the blue point is at a height, the blue point is at 10 over, and then it's up at a height of 3 plus dy, so 3.16 repeating. The actual value is at 10 square root of 10, and the square root of 10 is 3.162. So you notice that this guy is the actual value, this guy is the approximation using a linear, it's a linear approximation. So we came up with a number that's very close to the square root of 10. Okay, this is the actual square root of 10, but we came up with a number that was close to the square root of 10 by using the tangent line as an approximate.